Hello everybody, welcome back to physics. This is video lecture 19.4, our last lecture for chapter 19 in our book, and we're going to be studying section 9 in chapter 19, which is all about an adiabatic process with an ideal gas. It says expansion there, and we'll talk mostly about that. So we're talking about an ideal gas in a container that's going to expand, its volume is going to get bigger, but it's going to be specifically what's called an adiabatic process. But I will also mention from time to time how what we're talking about can also be applied to an adiabatic compression, where the volume gets smaller. Okay, first let's remind ourselves what that word adiabatic means, because it's not an everyday word. So we have to be clear what the definition of that is. Here's the reminder. That word adiabatic for any thermodynamic process means, and it means nothing more or nothing less than Q equals 0. Remember, Q represents energy transferred as heat. So adiabatic means no heat transfer between the system, the ideal gas, and its surroundings. How would you do that with our ideal gas apparatus that we've been talking about for these two chapters? Here's a schematic of it in cross-section. You have the cylinder with the gas inside and the piston on top with the lead shot, and then all the sides have been thermally insulated. Okay? This brown stuff is thermal insulation that's surrounding the gas, including the piston. All right? That thermal insulation prevents the environment from exchanging energy as heat. Notice there's no hot plate thermal reservoir at the bottom. Okay? It's all thermal insulation. That's how you get Q equals 0 in a lab situation. It also happens out in the natural world, normally, without us doing anything special. How does it happen there? It's usually because the process with the gas happens so rapidly that it's over before there's time for energy exchange as heat. So we don't really worry too much right now about how we get it to happen. Let's just study what happens to an ideal gas if Q equals 0. Let me emphasize in this lecture, because here's the tip that can get people. A lot of people interpret adiabatic, Q equals 0, to mean isothermal, which by definition means delta T equals 0. And all I can emphasize over and over and over again is that those two things are not the same. Q equals 0 and delta T equals 0 are not the same. They're not interchangeable. You can't think of one as being the same as the other. In fact, what I want to show you here is that if you have an adiabatic process with an ideal gas, it absolutely physically cannot be isothermal. And we can use the first law of thermodynamics to help us see why. Okay, so we're going to also use PV diagrams too. Okay, so I'm going to talk about actually both adiabatic and isothermal processes because I want to contrast them. Okay, so let's have a PV diagram. It's over here on the right, pressure plotted versus volume. And let's have a starting point right there. That big dot in the PV plane represents an initial volume. That might be rather small, so we'll label that V initial, and some initial pressure. And we're going to let the gas expand to a final volume out here, V final. All right, now actually first, I want to talk about an isothermal expansion. Remember, I'm going to contrast these two. So let's first talk about an isothermal expansion for an ideal gas. And again, isothermal means delta T equals 0. What are the consequences of that? First, from the previous video lecture, this is a very handy formula to remember for an ideal gas, that there is a very simple result for the change in the internal energy of an ideal gas. And it's generally valid. There's no restriction on it other than it's an ideal gas. And the change in the internal energy of the ideal gas is given by F/2, little n, number of moles, big R, gas constant per mole, times temperature change. Let me remind you over here to the side that F stands for the number of degrees of freedom of the molecules, of each molecule that makes up the gas. We'll have to know that. But that's a very handy formula for an ideal gas, change in internal energy. And let's apply it to an isothermal expansion of an ideal gas. Well, since isothermal means delta T equals 0, that part right there is 0. So the internal energy change is 0. The internal energy doesn't change in an isothermal expansion. And so the way that would happen on the PV diagram, if it's isothermal, is that the PV diagram would start at the initial point and then follow the isotherm that passes through that initial point. And I've labeled that isotherm as the T1 isotherm, and it's there in blue. So the process, the PV diagram for going from V initial to V final, for if it's isothermal, would be along this path. There's the arrow, which is an isotherm going from V initial to V final. And the isotherm is given by the formula P equals a constant over V, where the constant is N times R times whatever the temperature is. NR, in this case, T1. Okay? Which, remember, is the formula for an hyperbola. Now, let's go back. Okay, so that's a PV diagram for this process. Let's go to the first law of thermodynamics. Let's apply that. It's got to be true. Start with delta E internal equals Q minus W by, but put in what we just learned. If it's an isothermal process, delta E internal is 0. So put the 0 on the left. And then just rearrange and you get a very simple result and a simple conclusion. If it's an isothermal process, whatever energy transferred as heat Q is going to equal however much work is done, W by. The Q equals the W. Now, if we're talking about an isothermal expansion, the W by, of course, is greater than 0, because that's what happens in an expansion. So we must conclude that there has to be a Q greater than 0 for an isothermal expansion. Notice Q greater than 0, not adiabatic. Okay? If you want to go from the initial point at V initial to the final volume, V final, along that isotherm that I've sketched in blue, but you don't want the temperature to change, that's what it means to be on an isotherm, you are going to have to add heat as the gas expands. You have to do that. It's not adiabatic. Okay? Now that's an isothermal process. Okay? All right. Now let's reset the gas to the initial point. Okay? With the initial volume VI, that dot there on the PV diagram. But now let's use the apparatus that's thermally insulated so that it is an adiabatic expansion of the ideal gas. Okay? All right, so we're going to use a thermally insulated container, and we're going to want it to expand. Now we have no heat plate, thermal reservoir at the bottom, so the only thing we have at our control is the lead shots. So we have to figure out how to get the gas to expand with the lead shots. You can think about that a minute. Now, the only thing that seems intuitive would be to take a lead shot away one by one, thereby reducing the pressure and letting the volume get bigger. But however you would do it, the point is you have the gas expanding, but you don't allow any energy transfer as heat because you've insulated your container. And that would be then called an adiabatic expansion of an ideal gas. And by definition, that means Q equals 0. Okay? Let's figure out the consequences of that with the first law of thermodynamics. So your starting point is the statement of the first law, delta E internal equals Q minus W by, but now it's adiabatic, so it's the Q part that is put in as 0. You got to put the 0 in the correct slot. And so then the conclusion you draw from the first law is this line right here, that the internal energy change of the gas will be equal to the negative of the work done by the gas. But again, our gas is going to expand, so W by is greater than 0. So on the right-hand side, I have a negative sign times a positive number, so delta E internal is negative for an adiabatic expansion. But then remember the formula that delta E internal equals F over 2 times little n R delta T. And so if delta E internal is less than 0, then delta T must be less than 0. So the temperature goes down in an adiabatic expansion. It can't be isothermal. Absolutely cannot. If it is adiabatic, it cannot be isothermal. If it's an adiabatic expansion, the temperature will go down. Let me show you that back up on that PV diagram. I've got the new curve drawn, but I'll highlight it for you. Again, we're starting at the initial volume, at the initial point, and we're going to end up at the final volume, VF. But now we have to end up, we can't be on the T1 isotherm, right? Because it's not isothermal. In fact, we have to end up at a lower temperature than T1. So our curve now has to go below the T1 isotherm. And so I'm just going to sketch what it looks like right now, and I'll tell you how to get the equation of that curve in just a second. But it looks something like this. Comes down, and it's gone below that T1 isotherm until we get to the final volume. Okay? That's the appropriate path in the PV diagram for an adiabatic process. So here's the description. Adiabatic expansion of an ideal gas follows that path that I just drew in green. And in fact, it ends up on an isotherm that I said is the T2 isotherm, temperature 2, where T2 is less than T1. The temperature of the gas got less. All right, now, again, let me emphasize. The formula for the isotherm, such as the T1 isotherm in the PV diagram, is P equals a constant over the volume. I'd like to know the formula that describes the new curve for the adiabatic process, the one I've drawn in green. Different formula, okay? I'd like to know what that is. Let's go now back to the second slide. And I've got another PV diagram here, similar to the one I just showed you. It actually shows 3 different isotherms that happen to actually have actual temperatures labeled, 700, 500, and 300 Kelvin. Notice the higher the temperature, the higher up the isotherm is. And it shows a sample, an example curve for an adiabatic process that starts at some initial point I and ends at some final point F. And it shows that part of that curve that takes the system from I to F, right there, if it's adiabatic. And notice that the adiabatic curve goes from a higher isotherm to a lower one, meaning the temperature goes down. But I come back to my question, what is the equation for that curve in green, where it has the red part also shaded in? It's called, that curve, an adiabat. Just like the curves for isothermal processes are called isotherms, the curve for an adiabatic process is called an adiabat. What is the What is the equation? What is the formula for an adiabat? We need to know that, okay? All right, I'm going to tell you what that is. Now, I'm not going to derive it. I am going to say that because it takes a number of steps. You can read in your book. Read section 9, chapter 19 on Wiley Plus. And they will go through the derivation for you. You need the first law of thermodynamics, and you need the ideal gas law, and of course you have to stipulate that Q equals 0. And I'm just going to tell you what you can learn. You can get a very helpful relationship between the pressure and the volume of the gas if it's an adiabatic process. Remember now, what we're about to write is only valid if Q equals 0. And it's an ideal gas. Are you ready? Now it looks a little odd, but it is useful. It goes like this. Take the initial pressure times the initial volume, but raise the initial volume to an exponent labeled gamma. And then that must equal the final volume, the final pressure times the final volume, where the final volume is also raised to the gamma power. There's an exponent gamma. What is that exponent gamma? That's important. Again, the derivation in the book will show you that that exponent gamma is the molar specific heat at constant pressure for the ideal gas divided by the molar specific heat at constant volume. CMP over CMV. And we have formulas for those, simple formulas. For CMP, F over 2 plus 1 all times R. And for CMV, it's F over 2 times R. And so the factors of R cancel. And then all I did is multiply numerator and denominator by 2. And I get a very simple expression for that exponent gamma. F plus 2 over F. Remember, F is the number of degrees of freedom that the molecules of gas have. Number of degrees of freedom. So, for example, if you have a monatomic gas, like helium, then the only degrees of freedom are translating through space, and space is three-dimensional, so F equals 3. If it's monatomic, I just abbreviated there. If they're diatomic molecules, you always have the 3 translational degrees, and if it's very cold diatomic, that's all you have. But if it's room temperature diatomic, you've got the 3 degrees from translation, degrees of freedom, and 2 degrees of freedom from rotation. So 5 if it's diatomic with rotation. And if it's diatomic, even higher temperature, with vibration as well, you pick up 2 more for 7. Okay? So rotation plus vibration. And those are basically the cases you'd have to worry about. But no matter what F you put in, 3, 5, or 7, or even something else, it can't be any smaller than 3. Gamma is F plus 2 over F. So gamma is always greater than 1. So now let me show you the formula for that adiabat, because it's going to come from that pressure-volume relationship right up there. So let me kind of erase things so I'm back to that. Note that another way to say that pressure-volume relationship, I'll write it over here to the side, is that the pressure times the volume. Okay, I'm back. There was a little technical glitch. The formula relating pressure and volume for an adiabatic process can be written like this. Pressure times volume to the exponent gamma equals some constant. That's what P initial, V initial to the gamma equals P final, V final to the gamma means. The pressure times the volume to the gamma power, that combination is always equal to some constant. So the formula for the adiabat is pressure equals constant over V to the gamma power, where gamma is greater than 1. And so that gives you a curve that falls down more steeply than a hyperbola. Remember, the isotherms are hyperbolas. This curve falls down more steeply than that because it's C over V to a power greater than 1. And so the adiabat drops down more sharply, more steeply than an isotherm, and ends up going to a lower temperature isotherm. Okay? Now, there's another version, there's a way to rewrite the pressure-volume relationship right here in an adiabatic process that can be helpful in solving problems. And all it is saying is, what if you have a problem where you have an adiabatic process in an ideal gas, but it doesn't give you pressure and it doesn't ask for pressure. Instead, this problem is concerned about volume and temperature, because that could be pretty common as well. In that case, our adiabatic relationship between P and V isn't that helpful. But we can use the ideal gas law and that P-V relationship and get a relationship between T and V for an adiabatic process, and that would also be helpful. So we need to know the temperature-volume relationship for an adiabatic process with an ideal gas. I'll just show you briefly how you do it, how you get it. It's not hard. Just use the ideal gas law and write P initial equals nRT initial over V initial. And substitute that right there. And then do the same thing for P final. Okay? P final equals nRT final over V final. And substitute that for P final. And when you do that, you'll have something that looks like this. Let me just write it right here. nR T initial, V initial to the gamma over V initial equals nRT final, V final to the gamma over V final. Then cancel the R and the T, and then note on the left that you have a V initial to the gamma upstairs and a V initial to the 1 power downstairs. And those can be combined to have V initial to the gamma minus 1 power upstairs. That's this. And then on the right-hand side, you'll have T final times V final to the gamma minus 1. So that's also a useful little formula, but it relates temperature and volume in an ideal gas for an adiabatic process. But be careful. There's a subtle difference between the pressure volume and the temperature volume formulas, specifically with those exponents. Gamma in the pressure volume case, gamma minus 1 in the temperature volume case. Now we're going to be talking about that in class, adiabatic process for an ideal gas, but I will just mention briefly that you could also have an adiabatic compression of an ideal gas. You could have the gas in the insulated container, and you could have the piston go down, making the volume less, right? That would be an adiabatic compression. Let's get myself some room here. Let's look at that on our PV diagram. The way I could represent that in my PV diagram is just change my labels. Let's start down here and call that point I, and end up here and call that point F, initial and final. And compress, make the volume smaller in an adiabatic way. And then you follow that same red curve, but going to the left and up. And then you notice you cross isotherms going upward, so the temperature of the gas goes up in an adiabatic compression. Okay? So if you compress a gas adiabatically, its temperature goes up. And this is actually quite noticeable. Common example people quote is the bicycle pump. If you're pumping up a bicycle with the old-fashioned pump that you pump manually, you're doing that pretty quickly. It's adiabatic, You touch the side of that pump, it's going to be warm. Okay? There's also something called fire starters, which were used in antiquity, which used an adiabatic compression of air to create a spark and then use that to start a fire. So an adiabatic compression will make the temperature of the gas go up. Okay? All right, the last thing in the video for today is to give you a little practice. So this would be, of course, class engagement. On Blackboard. And with the practice with adiabatic process and an ideal gas, it goes like this. We have, as you can see, a PV diagram, rather simple, standard looking one. And there's a dot in the figure to represent the initial state of a gas. Okay, there it is right there. And the curve you see in red, which of course goes on this way, dot, 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 and on this way, dot, 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 is not an isotherm, watch out, it's an adiabat. It's that adiabatic curve through the dot, and that divides the PV diagram into regions 1 and 2. Region 1 is below the adiabat, the adiabatic curve. Region 2 is above. Then we're going to give you 4 processes down here, A, B, C, and D. For each of these processes, you are to determine and state whether the corresponding heat transfer, Q, is a positive number, a negative number, or 0. First case, the gas moves up along the adiabat, up that way. Second case, it moves down along the adiabat from the starting point, that way. That's case B. Case C, it moves to anywhere in region 1. I'll give you a hint to help you on your thinking. Suppose you start at that dot for the initial state, and you follow the isotherm that passes through that dot. You might want to think about, look at some of the drawings I've had in the lecture here. What would a sketch of the isotherm through point 1 look like? Okay? And let's say for C and D, that you follow the isotherm that passes through the dot. In part C, you follow that isotherm that leads you into region 1. And in part D, you follow the isotherm through the dot that leads you into region 2. In all those cases, A, B, C, and D, you have to tell me whether Q is a positive number, negative number, or 0. Okay? All right, so that's what you do on Blackboard. And that's all for this video.